Hello, dear students. Welcome to this new lesson under the chapter Logic Gates. Welcome to the Bye channel. If you have not yet subscribed to this channel, make sure you do so to have the latest update about the chapters in advanced level ICT, advanced level computer science, and ordinary level computer science, be it theory and practical. Okay, today under the chapter Logic Gate, we shall be seeing what we call the Karnaugh map. Remember in the last lesson, we saw that after obtaining the sum of product and the product of some expression of a particular output from a truth table, there are two ways the expression can be reduced, either using Boolean identities and De Morgan's theorem or by using Karnaugh map. Okay, the first method, which consists of using Boolean identities and De Morgan's, has already been covered. And today we are to cover the alternative method which we call the Karnaugh map. Karnaugh map or K-map are powerful visual tools for carrying out simplification and manipulation of logical expressions having up to 5 variables, supposed to be 4, having up to 4 variables. The K-map is a rectangular array of cells where each possible state of the input variables correspond uniquely to one of the cells and the corresponding output state is written in each cell. If applied correctly, a K-map produces the simplest possible form for the Boolean algebra expression. The standard Karnaugh map for 2, 3, and 4 inputs are given below. Sorry. So as said and highlighted, simplest possible form of a Boolean expression. So if we correctly apply the Boolean, if we correctly apply the K-map, our result will give us the simplest possible form of a Boolean expression. Remember that when we were using Boolean algebra, we saw some cases where we thought that the answer was already simplified, whereas it could be further simplified. But with the K-map, if correctly applied, our result will always be the simplest possible form of a particular expression. Now, for a two input, this is how the K-map looks like. So my two input here are A and B. I have A at position 0, A at position 1. Same thing here, same thing here. Remember that in our first lesson, our first nota bene, we saw that if we have I number of inputs, then the different possibilities is 2 to the power I. So here, as I have two inputs, A and B, it means I should have 2 to the power 2, which is 4 possibilities. That is why I have 4 empty cells here for the different possibilities. At this level, when A is 0, B is 0. At this level, when A is 1, B is 0. At this level, when A is 0 and B is 1. And finally, at this level, when A is 1 and B is 1. In case of a 3 input, we are supposed to have 2 to the power 3, which is 8 possibilities. And these are the possibilities, 4 up, 4 down. And we have the different states. A 0 or 1, B and C. So this is the value of B, this is C, this is B, this is C, this is B, this is C, this is B, this is C. Now, questions that students usually ask that, sir, yeah, I have A being 0, then we have 1. For BC, is it not normal for it to be moving accordingly? Because when we convert this, we realize this is 0, we realize that this is 1, this is 3, and this is 2. Why is it that there is 3 before 2? Students always ask this question. And let me give you the correct answer. On a K-map, the change in bit that we observe must be of 1 bit only and never 2. Let me explain myself. From 0 to 1, you see that this 0 is which is the only bit has changed to 1. From 0, 0 to 0, 1, you realize that it's only the bit on C that has changed to 1. B remained the same, whereas C has changed. From this to this, you realize that B has changed, but C remained unchanged. From this to this, we see that B remained unchanged, whereas C has changed. If it's that we were living from 0, 1 to 1, 0, we realize that B will change and C will also change, which will make our map to be wrong. On a K map, the change in bit we are to observe must be 1 bit at a time. So we cannot be living from a particular input and the next input there is a change in 2 bits. This will not go, and these are some of the rules that we have on the Karnaugh map. the change in bit should be of single bit. For a 4 input logic gate, this is what we are going to have: 0, 0, 1, 1, 1, 1, 0. These are the inputs of C and D, whereas these are the inputs of A and B. Okay, let's proceed. The interpretation of a K-map follows these rules. Only cells containing ones are considered. Very, very important. When we shall be seeing the K-map, we shall consider the cells only where 1. We shall consider the cells containing the value 1. Next, as you can see, if I have this particular case, I am going to consider only this cell and this cell, because these are the only cells where we have a 1, whereas here we have a 0. So we are not going to consider these particular cases. Next, groups of cells containing ones are identified where possible, with a group being a row, a column, or a rectangle. Very, very, very important. Let me repeat. Groups of cells containing ones are identified where possible, with a group being a row, a column, or a rectangle. So for example, if I have this particular case, realize that as you are having 1, 1, 1 and 1, it means that these particular cells are 0. It depends on you. You can put the 0 as well as you can allow it to be blank. Personally, I prefer it to be blank in such a way that I will not be confused. Good. In this case, how are we going to group it? 1. These are the two ones that I'm grouping so that it is horizontal. I have a row. The next, I can group vertically, as you are seeing those two ones. I will as well group from the different ends, that is, as it begins here, it ends here, and these two are connected. So it is possible for me to group this one and this one for it to form what? A sort of rectangle. Good. Now, guys, is it possible to group this particular one? Yes. Why? No. Why? Give your reason. Okay, remember we said groups of cells containing ones are identified where possible with a group being a row, a column, or a rectangle. So in case of a diagonal, it cannot be possible. We don't group ones diagonally, only horizontally or vertically, as you can see. The next condition, groups must contain 2, 4, 8, and so on. So in case you might not understand this point, what we are saying here is that the groups of one we are containing must contain multiples of 2. As here, you see that here it contains 2, that is this and this 2, 2, this and this one 2. Each group should be as large as possible. Now, you might ask yourself, why can I not contain 1, 2, and 3? If I come back to the previous reason, you realize that if I take this, this, and this, it will make 3, and it's not possible. Each group must be a power of 2. And now this new point says each group should be as large as possible. Take an example with this one. What am I going to have? Instead of taking these two, and these two, it is not going to give you a good simplification, because remember here is precise if applied correctly. That is, you can apply your K-map and at the end the result is still simplifiable. But if you apply correctly, what you shall have won't be the case. So at this level, you realize that I have 4 ones and I have these 2 ones. So instead of taking these 2 and these 2, I prefer to take all these 4 at once. So this is not correct. Otherwise, this is what should be done. You group the 4 ones directly and you group these particular 2 ones. Now you ask yourself, why are you considering this and this again? I am considering these 2 in such a way that this will go with this particular input. Okay, so I group these 4. So rather than grouping these 2 and grouping these 2, I prefer to group these 4 directly. Then I group this one in such a way that in this my particular combination, this one goes with this one, because this one was empty when I grouped the first 4. Next, groups can overlap and all overlapping groups must be used. When we say groups can overlap and all overlapping groups must be used, an example is this one. You realize that this group and this group overlap at this one. The blue and the green overlap at this position. The green and the yellow overlap at this position. So groups can overlap and there is no problem with that. Good. If an individual cell cannot be contained in any group, it is treated as being a group. Let me take it all over. If an individual cell cannot be contained in any group, then it is treated as a group. Take an example with this one. Take an example with this particular one. You realize that I have one here and here. So remember, groups can be identified in a row or a column. So grouping diagonally will not go. Instead, what will I do? Since there is no vertical group that can go with this one, no vertical nor horizontal, same with this, what I will do is that I'm going to apply this particular rule. Okay, before going there, look at this particular one that we had here. After grouping these four, this one was alone. But since this one could be paired with this one, for me to have a vertical rectangle, that is why I grouped it as you can see. But with these two, there is no way for me to group this and this rather than diagonally, and diagonally is not a way of grouping digits here. So instead, I'm going to take each individual cell as a group, as you can see. So I will consider this and I will consider this one. Good. Within each group, the only input values retained are those which retain a constant value throughout the group. Okay, let me explain this one very well. Within each group, the only input values retained are those which retain a constant value throughout the group. Now, let us use any of these as an example. But before we proceed, take note. If the retained input has logic value 1, it is not complemented. But if it has value 0, it is complemented. So it's that this is similar to the sum of product expression. Let us proceed. If you consider this particular case, let us take this particular case for you guys to better understand this point. Okay, you realize that this blue is giving me B bar C. Why is it giving me B bar C? Let us understand it very well. In this group, what do we have? In this particular group, what are we having? We realize that at this level, B is 0, C is 1. In this particular group, A has two values because at this input, A is 0, at this input, A is 1. We realize that the transition from this input to this input, A is changing values. And this one says within each group, the only input values retained are those which retain a constant value. So A is eliminated. Let me take it back. At this particular one, what is A, B, and C? A is 0, B is 0, C is 1. At this particular value, A is 1, B is 0, C is 1. You see that A is changing because the value of A here is 0, the value of A here is 1. Whereas the value of B and C, both here and here, are the same. So this implies that only B and C will be retained. But now, in this particular group that we did, what is B? B is 0, so it is complemented as said here. Whereas C is 1, so it is not complemented. That is why this group gives us B bar C. Let me take it all over for you to understand better. If you have a vertical group, first of all, when you are having a group, identify the values of the different input at those values. The different group you have here are this and this. And we realize that from this input to this input, A is changing because A leaves from 0 to 1, so it is eliminated. Whereas from this value to this value, BC remains the same and B is 0, so B bar, C is 1, so C normally non-complemented. That is why here I have B bar C. We go to the next one. The green will give me A bar, B bar. Let us understand why. The green is taking this input to this input. Okay, from this input to this input, we realize that A is the same because at this level, A is 0. At this level, A is still 0. And since it does not change, it is retained. Being at position 0, it is complemented. Are we together? Good. Let us proceed. From here to here, you realize that the value of b is 0. At this level, b is 0, so b is unchanged. And since it is at position 0, it is complemented. At this level, what is c? 0. What is c at this level? 1. You see that c is changing. That is why it is eliminated. So this is very important. After placing these different bits and grouping, make sure you carefully identify the input that is changing and you eliminate it. Then for those that are retained, identify their values and complement them if they are at position 0 and maintain them if they are at position 1. Okay, for the yellow one, can you give me the expression? Okay, C is giving me A bar, C bar. Let us understand why. First of all, the yellow is taking this bit and this bit, that is this and this. At this level, what is A? 0. What is A here? 0. So A has not changed. We maintain A. And since A is at position 0, it is complemented. At this particular value, what is B? B is 0. At this one, what is B? B is 1. So B is changing. We eliminate it. At this level, what is C? 0. Yeah, what is C? 0. So C remains unchanged. And since it is at position 0, it is complemented. So we have A bar, C bar. And now our expression is going to be the sum of these different expressions. So our output is going to be A bar, B bar plus B bar, C plus A bar, C bar. That is how we obtain the expression of a particular Boolean expression. Now, you can see factorize, but it does not change your answer because A bar has been factorized here and here, but it does not affect the answer because you could see factorize B bar from here and here. So it does not change anything. Don't forget to like, subscribe, and share. Okay, let's proceed. Still under Karnaugh maps. Example 1. Consider the following truth table. Obtain a reduced expression for the output. Now, one thing is that once you have the truth table, it is very important for you to know how to map the truth table to the Karnaugh map. Let us proceed. Here it is a Karnaugh map with 3 input. So what do we have? Using sum of product, we identify first of all where we have ones, as you can see. At this level, this level, this level, and these two. Now remember that for the SOP, I said in the previous lesson, first of all, identify where the output is 1. After identifying, we obtain a combination of the input. We complement the input if they are at 0, and we maintain them if they are at 1. So for this particular one, all of them are at 0, so they are all complemented. A bar, B bar, C bar. At this level, only B is complemented. Only B is non-complemented. So I'm going to have A bar, B, C bar. At this level, only A is complemented because it is the only one at position 0. So I will have A bar, B, C. At this level, only C is complemented. So I'm going to have A, B, C bar. At this level, none is complemented. So I'm having A, B, C. Okay. So that is our expression. A bar, B bar, C bar plus A, B, C bar plus A bar, B, C plus A, B, C bar plus A, B, C. Now, this expression can be simplified by either using Boolean laws or K-map. Method 1. Let us be using Boolean laws. Remember that for Boolean algebra, I told you that when you are reducing, it is very important for you to be able to identify those particular expression where you can factorize and go and have a very good expression. At this level, we realize that at this level, I can factorize A bar C and A bar C from this and this in such a way that B bar and B will cancel. Also, I can factorize AB from this expression and this expression. This is what I am going to have. That is A bar C bar into B bar plus B, AB into C plus C bar. We realize that in the important law, an input plus its inverse gives us 1, as you can see. From the identity law now, 1 times anything gives me the same thing. So I'm having A bar C bar plus A bar B C plus AB. Now, at this level, what can be done? We realize that we can factor A bar from this level and this level. So I have A bar into C bar into BC. And now you remember the proof we had the last time where it was said if you have an input plus its complement, because if C bar is my input, then its complement is C. So if you have an input plus its complement added to another input, then your result will simply be that input plus the other input. So I'm supposed to have C bar plus B. This is the proof as you can see. And so yeah, x is like my C bar. So if x is C bar, therefore x bar is simply C and my y is B. So I'm supposed to have x plus y bar, that is C bar plus B. So this is what I am going to have. I expand the bracket again. I'm going to have A bar C bar plus A bar B plus AB. And now at this level, I can factor out B. So I'm going to have A bar C bar plus B into A bar plus A. And input plus its inverse, 1. 1 times any input gives me back the same input. So this is the factorized expression of F. And this was using Boolean laws. Method 2, let us use Karnaugh map. This is our Karnaugh map with 3 inputs as we saw earlier. Now let us see how to map it. You will simply identify the expression where you use the SOP. That is this the first one. A is 0, B is 0, C is 0. So we are here. A 0, B 0, C 0. At this level, A 0. So we are on this row. A 0, we are on this row. B1, C0. B1, C0. So this is where we are entering. At this particular one, can you identify the cell? A0, we are on the first row. B1, C1, so we are entering here. Good. At this particular one, A is 1, so we are on the second row. B1, C0, 1, 0, so we are entering here. And for this last one, all of them are 1, so we enter at this level. So that one, as you can see, that is the input. That's what we have. Good. Now, how can we group the cells? Remember that when grouping, we must group the largest possible group that we have. So I am going to group this particular one because these are a group of 4 cells. As you can see, this is the first group I'm going to take because rather than grouping these two and these two, or grouping these two and these two, I can directly group these 4 groups. I hope you are together. Okay. Now, I can also group this one and this one, that is from this end and from this end. That is what we are having. Because instead of grouping this one alone, we see that this one goes with this one. So take this end and this end as if they are connected. So this one goes with this one. So these are the only 2 possible groups that we have. Now let us try and obtain their expression. It is true that for a rectangle with more than 2 inputs, it's a little bit complicated. But now let us understand it very well. Okay. From this input to this input, we see that A is changing because at this level A is 0, at this level A is 1, so it is changing. Now let us check for B and C. From this input to this input, B remains the same because B at this level is 1, B at this level is 1. Same thing for this one and this one. From this input to this input, C is changing because C leaves from 1 and it becomes 0. So C is changing. So for this red, we see that A is changing and C is changing, and we are left only with B. And what is the position and what is the value of B? B is 1. So this red rectangle gives us, so I instead started for the green one. For the green one, there is nothing obvious, there is nothing difficult here because we are moving from this input to this input. And now on this input, A is 0. At this level, A is 0. So A remains the same. And since it is at position 0, A bar. At this level, B is 0. At this level, B 1. So B is changing. We eliminate it. At this level, C is 0. At this level, C is 0. So we maintain C. And since C is at position 0, it is being complemented like A. So this green one gives me A bar, C bar. And for this red, already explained, I'm simply going to have B. And that is how I have my F is equals to A bar, C bar plus B, as you can see here. So that is how easy the Karnaugh map is. And if applied correctly, like we did here, we shall have a very reduced expression. So with the Karnaugh map, the first thing, make sure you identify your SOP expression very well. From there, map it to the Karnaugh map. From there, henceforth, group the digits as large as you can, as you saw with the red rectangle, with the red square if you want. That we have. Instead of grouping two rectangles of two input, I rather group the square. And we saw that it finally gave me B, and the green one gave me A bar, C bar. So my output is A prime, C prime plus B. Example 2. Consider the Karnaugh map shown above. Use the map to create a reduced Boolean algebra expression of the output. So in this case, you have a Karnaugh map already. It is just like you were given a truth table and you mapped already. This exercise was for you to carefully understand how the grouping is being done. Okay, what do we have here? A Karnaugh map of 4 inputs. How do we group it? The first group, as you can see, my square. So this is my first square I have. And now, can you deduce the value of this square? This square gives me A bar C. Let us understand why. From this input to this input, first of all, realize that when you are grouping a square, when you are checking for this one, you are checking up and down. But when you are checking these particular ones, you are checking left to right. So let us start with AB. From this input to this input, A remains 0. You see very well, A remains 0. So we maintain A. B is changing. So we discard B. We maintain A. And since A is at 0, it is complemented. We check now for C and D. For this input to this input, what do we see? C remains the same and C is at position 1, so it is not complemented. Whereas D is changing 1 to 0, so we discard D. So that's why this one is giving us A prime C. Okay, at this level, rather than just grouping these two because they are left, I can still group this. Remember that it is possible for us to have overlapping groups. If I group these two, it will give me an expression which can be factorized again. So I prefer to have an overlapping group of 4 cells, as you can see. Now, can you guys deduce from this to this? What is happening to A? What is happening to B? Who are we discarding? Who are we maintaining? The one we are maintaining, is it complemented or not? From this to this, who is changing? Who are we discarding? The one we are maintaining, is it complemented or not? So, after answering this question, we realize that this second square is giving us BC, because from here to here, we see that A is changing from 0 to 1, but B remains the same. B remaining the same is at logic value 1, so it is not complemented. From here to here, C remains the same, is at position 1, so it is not complemented, whereas D is changing, so we discard D. Okay, which other group can we have? Tick tack, tick tack. So we can have this particular group, that is this starting like this and ending at this level. Okay, now for this particular one, you realize that the bit can only move from top to bottom. As it can move from top to bottom, it means that CD remains unchanged, because at this level, C and D are 0. At this level, C and D are also 0, so they are maintained. And since both of them are at position 0, they will be both complemented. Okay, at this level, what is A? 0. At this level, what is A? 1. Since A is changing, we discard it. What is B here? 0. What is B here? 0. So we maintain B. So what we are maintaining are B, C, and D. Each are position 0, so they are complemented, and we get B prime, C prime, D prime. So our output in this case is going to be A prime, sorry, it's supposed to be A prime C. This one is not there. A prime C plus BC plus B prime, C prime, D prime. So that is how Karnaugh map is efficiently used. We shall come back to this when we shall be treating pass GC